In this lecture, we'll extend from our last conversation about the three different representations of probability distributions to two more concepts: random number generation and Monte Carlo simulation. We'll then use Monte Carlo simulation with Excel to demonstrate the central limit theorem, which is essential to much of statistical inference. In previous lecture on the three representation of probability distribution, we look at two generic variables x and y. Now we'll look at a very special variable called a continuous uniform random variable. Let's denote it as u. It has the same density between 0 and 1. And in order for the total probability to be 1, we know the density is also at a level 1 across the range of 0 to 1. You can also easily verify the cumulative probability for this variable is this 45-degree straight line. Also, the inverse cumulative probability is also a 45-degree straight line by flipping these two coordinates. This variable is really special for two reasons. The first reason is we can generate numbers that has this specific distribution by some special formula. So what happens is this special formula can produce a long string of digits, one after another, with no patterns whatsoever to them, like this one shown here. We can then chop these strings into, say, group of 5 digits, like this. And then we can just simply put a decimal point before each group, like this. So this process can continue. So by doing so, we are creating a number. We can create a sequence of variables that follow this particular uniform distributions. So the first number will be somewhere here, 0.20. The second number will be somewhere here, 0.56, and the third number will be somewhere here, 0.67. So this is the basic notion of random number generation. It's also called pseudo-random number generation because this sequence of digits are coming out of a formula. Therefore, they are not really random, but there's no discernible patterns to it. And because there's no patterns discernible, the chance for each of the 10 digits, namely 0 to 9, to appear at the first decimal place is 1 over 10. Same is true for the second decimal place to take on the value of 0, 1, 2 to 9, so on and so forth. Therefore, the end result is a sequence of numbers that are evenly distributed between 0 and 1. And you can increase the decimal places by chopping the string into a longer group, such as a group of 10 or a group of 15 if necessary, to generate random numbers with sufficient amount of decimal places. Pause the video and think about it for a bit to see whether this is true. The other reason that this is a very special random variable is its cumulative probability distribution is the same as the inverse, which is not the case for any other random variables. And this happy coincidence turns out to be very useful. It's useful because it allows us to generate all different kinds of random variables, discrete or continuous, as long as their distributions are known. I'll explain what I mean by picking up where we left off from a previous video at the inverse cumulative distribution. So this is the example that we used in a previous video. We have two variables, x, a discrete variable that can only take on 4 values, a, b, c, and d. Y is a continuous variable that can take on value in this range. And these are their corresponding cumulative distribution and inverse cumulative distribution. Now I'm going to describe to you a mapping mechanism based on these two inverse cumulative distribution coupled with the inverse graph for the uniform variable. So it goes like this. I will use the pseudo random number generator to produce a u value. For example, say u equal to 0.40633, and then it should be somewhere here. Then it will be reflected by this 45-degree line to the same value of 0.40633, but this time as the cumulative probability. It will then go up, and because the value is between 0.3 and 0.7, if you continue this upward, it's going to be captured by this segment where I just put a dashed line earlier, which will then be mapped to the value of c. So this way I just establish a mapping relationship for u equal to 0.40633. I produce another value which is x equal to c. Let me give you another example. Let me say generate another random number that is uniformly distributed. Let's say it's 0.78513. It will be somewhere here, which will be mapped to this axis to somewhere here. Again, which will be mapped to this axis to somewhere here. And then if you go up, since it's greater than 0.7, it's going to be captured by this segment, and in turn it's going to be mapped into another value of x equal to d. Now I can apply the same mapping mechanism to generate white. For example, I can generate a couple of u's like this, and similarly I can put in return I can generate a number of y this way. So say here y equal to m, and this value y equal to n, for example. Similarly, I can generate a lot more u's, say 1,000 u's this way. And as a result, we can produce 1,000 x's as well. Similarly for y. Now we know all these 1,000 of u values are evenly distributed between 0 and 1. Similarly here, Now, pause the video and ponder what distribution the resulting x and y follow. The answer is they are following the original distribution of x and y, which the inverse cumulative distribution are based on. Take x for example. The chance for x to be equal to c is 40% based on its probability distribution. And the chance for u to be between 0.3 and 0.7, thus generating a x equal to c, is also 40%. Because u follows a uniform distribution. So the same intuition applies to y. By the same token, this mapping mechanism will work for any random variable as long as the probability distributions are known. And this is why software such as Excel can provide random numbers, can generate random numbers that follow distribution that you specify. Now let's go to Excel to look at some examples. So in the Data tab, you can click on Data Analysis. If you don't have this, that means you need to find it from the Add-in menu. So once you click on Data Analysis, you should be able to find random number generation. Now here, it allows you to specify how many variables you want to create. I only want to create one here, for example. It also asks you to specify how many random numbers you're going to generate for that variable. I'm going to say 100 for now. And here is where you specify what kind of distribution you want the random variable to follow. So I will start with a binomial distribution, which is the familiar coin toss example. I want to have a fair coin, therefore it's 50% heads or tails. The number of trials, I would say 30. And the output range, I want to put that sequence of random number starting from here. And I will just click on OK. So I'm going to name this one as binomial of 30. And similarly, I can generate a bunch of other random variables follow different distributions. For example, let me also generate a binomial distribution with only one number of trial. That means you only flip coin one time. And then I'll move this to here. So this will be binomial of 1, flipping just one coin. So in this case, by flipping a coin 30 times, you could have 17 heads, 16 heads. These are the sequence of random number that follows that particular distribution. And this one is flipping one coin 100 times. So each time will be either heads, tails, 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 followed by heads, so on and so forth. Let's now generate a number of different distribution. Let's now try a Poisson distribution. And in one of our previous example, we had this problem of number of chips in a cookie, and the average number of chips in a cookie is 6. So let's put 6 here, and I will move the result one cell to the right. Now this is a Poisson random variable with the mean of 6. So essentially you are looking at 100 different cookies, and each number represents how many chips, how many chocolate chips are contained in that cookie. Let's try a number of continuous variable. Let me try a normal distribution with the mean of 0 and standard deviation of 1. Right, so this would be a standard normal z value, a standard normal distribution. So here it shows 100 random numbers that follow the z distribution. So this seemingly simple tool of random number generation actually allows us to study very complex system, which is the idea behind Monte Carlo simulation. I will give you a quick example before we move on to the central limit theorem. So in this simple diagram, we are trying to know how many cashiers represented as this to staff in a supermarket so that the waiting time for the customers are not exceeding 10 minutes. In this case, we just need to simulate two random variables. The first one is transaction time, which is how much time it would take for a cashier to check out a particular customer. The second random number we need to simulate is the arrival time between two customers. We can assume they follow certain distribution based on observation. And the function of random number generation in Excel, coupled with a bunch of other functions like if-then, could implement this simple case fairly readily. And that would actually allow us to estimate how quickly the line will build up so that the customer have to wait longer than 10 minutes. So this is just a simple example of Monte Carlo simulation, and which is extremely useful because it allows you to simulate what will happen in the future, make decisions, revising the decisions based on the simulation result without paying the price of making actual mistakes. A very complex and convoluted example of simulation that everyone knows about is the movie The Matrix. Here is the scene from the movie. Have you noticed the name of the book before? But the whole premise of the movie is that reality is nothing but a super high fidelity simulation. I certainly hope that reality is not a simulation, but surprisingly enough, based on the current understanding of quantum mechanics, reality in subatomic level can only be described with probability. I will take another short detour to give you a 3-minute introduction to quantum mechanics before we return to central limit theorem. This one-dimensional bell-shaped density function describes the likelihood of x to be located in a really small interval x density function. So the probability for x to be located in this small interval is represented by the area above it. This is the idea of density function we have come across many times. So, but if we extend this density idea to 2 dimensions, then this time we would actually have a bell, a real bell, compared to this, which is really a cross-section of a bell in a one-dimensional case. So we will have a bell to describe the likelihood for a point. In this case, it's 2-dimensional, so we would have x dimension and y dimension. So we can use this density function to describe the likelihood for a point to be located in a small square in this x and y plane. So the probability will be represented by the volume above this square, like this. But if we further extend this idea to 3 dimensions, we'll arrive at the quantum mechanics understanding of how an electron circulates a proton in a hydrogen atom. There's only one electron in this case. So the cloud indicates the likelihood of an electron to be located in that position in the xy z 3 dimension. So the denser it is, the more likely you would observe electron in that tiny cube in that 3-dimensional space. So this is the fundamental idea of quantum mechanics. Namely, our reality, once drilled down to the subatomic level, is probabilistic in nature. Let's now turn to the introduction of central limit theorem. I will start by generating 30 random variables. And for each of them, I will create 1,000 observations. And each random variable is going to follow the uniform continuous distribution between 0 and 1. And I will place all these random numbers starting from this position. So what you have here is 30 variables, each with 1,000 observation. Now I'm going to name each column starting from U1 to U2 until U30 to name each of the 30 variables. Now I'm going to calculate a number of statistics for the U30. Remember, all these 30 random variables are identical to each other in terms of distribution. I just created a number of statistics based on U30 and put them on the top portion. These statistics are the max, mean, the standard deviation, and the mean. Remember, these are the statistics based on U30 of 1,000 observations. Now I'm going to treat the 30 observation in one row as one sample. And then I'm going to calculate the sample mean based on this group of 30 observation by using simply the average function. And then I would name this column as U bar. I would then calculate the sample mean for each of the remaining 999 sample. Each consists of 30 observations. We'll use copy, and then I would select the whole range, the target range, and simply click on paste. So this way I have just created this new variable U bar. The reason this is a new variable is just like in the case where we add 2 dice to form the sum. which becomes a new variable. And the distribution of the sum of two dice is related to each single die. Similarly, the U bar, which is the average of a sample of 30, is also related to each of those individual variables. Now I'm going to calculate the same for statistics for the new variable U bar simply by copy the same formula to its right. Now we will notice that the mean of U bar, the average of a sample, is really similar to U30, the individual variable. But the standard deviation of U bar is a lot less than U30. What about the overall shapes of the two variables, U30 versus U bar? Histogram will be the right tool to visualize such overall shape of distributions. So here I just created the histogram of U30, and not surprisingly is more or less a flat line as we expected. How about U bar? Is it also going to be flat as well? You might want to pause and ponder for a while. Now I'm going to create a histogram for U bar. Remember, you need to use the maximum and minimum information of the variable to adjust for the proper bin size. So since in this case the minimum value is around 0.3, the maximum value is around 0.7, I'm going to create a sequence of numbers starting from 0.3 with the increment of 0.25. So the next number is going to be adding 0.025 to the previous number. And I will use Excel function auto filling the sequence by dragging this down until I get to 7. I just ran a histogram on U bar. Surprisingly, U bar is no longer a flat line, but is taking on a shape that is more or less bell-shaped. So what we just witnessed here is the central limit theorem at work. So the central limit theorem says if we take a sample of sufficiently large size, such as n, for example, n greater or equal to 30, in our case n equal to 30, if we take a sample of a random variable x of any distributions, so the x is associated with mu and sigma. X, we do not know what distribution it follows, but the central limit theorem tells us that x bar, the average of the sample that has the sample size greater than or equal to 30, x bar, the new variable, in our case the U bar, would now follow a normal distribution with the new mean being, I will use x mu sub x bar to indicate this is now the mean for x bar, the new variable. The new mean is the same as the individual mean, whereas the new standard deviation, now again denoted by sigma sub x bar, is related to the previous sigma this way. So this is what central limit theorem tells us, and we can quickly verify in this particular case. This is U bar, the mean is 0.49. In theory, we know it's going to be 0.5, and the individual variable, the mean is 0.49. Again, in theory, it should be 0.5. So they are really close to each other. The standard deviation of sigma sub x bar is this number, 0.05321. The original standard deviation is this number. We can quickly verify whether this relationship holds up. So I would take this value, the original sigma, and then I would divide it by square root of sample size. In this case, it's 30, which again is really close to the sigma sub x bar. So this is what the central limit theorem tells us is really useful, because since most of the time we would not know the individual distribution for any random variable, but thanks to the central limit theorem, we know the sample mean out of any arbitrary distribution will follow a normal distribution.